Hello everyone. So today we're going to go over chapter 12, basically all of it, which is correlation and regression. In chapter 11 we were able to determine if two um, qualitative or categorical variables were related, and now we're going to look and see if two continuous variables are related. So the concept is similar. You have some number of subjects, and for each one you collect samples on two variables, and you're going to organize that data not in a contingency table as was the case with chapter 11, but in a scatter plot as will be the case here. And what we want to know is there a relation between them, and is that relation statistically significant? Okay, so let's go ahead and have a look here. So I'm on the Canvas page under Pages, and I'm going to select the lecture notes. There it is, share this to Notability. There we go. Okay. So this is similar to what we saw in class, but they're not exactly the same. All right. So we're going to do correlation and regression with hypothesis testing, of course. Okay, so again, have you ever wondered if there is a correlation between these two variables? So remember, these are continuous variables. IQ, income, homework scores, exam scores, these are continuous variables. You can't just categorize them into, so these are non-categorical variables. A test for independence determines whether there's a statistical dependence between two categorical variables, but today we're going to talk about a statistical dependence of numerical continuous types of random variables. Okay, here's an example. Suppose we've got 30 randomly selected NBA players, and we have their height and weight, and we plotted them on the same scatter plot. So for each person, each player, we collect their height and weight, and then we plot their height and weight here. In this case, weight is on the x-axis, height is on the y-axis. So each player represents a single point. So for instance, this could be, somebody, maybe LeBron James or Steve Nash or somebody. And we plot a bunch of them. Now, the question of correlation is does the value of the weight tell you anything about what the height is? See, so if I knew that somebody's weight was maybe 175, does that tell me what their height might be? And I think that it does. This does suggest something. I'm pretty sure their height is not going to be up here. It's not going to be up here. It's probably going to be down here. Well, that's some information. Okay. When one has information about the other, when one has information about the other, I wish I fixed that. There is correlation. And when I say one, I mean one variable. When one variable has information about the other, there is correlation. Okay. So height and weight are correlated, but age and height are not correlated. So again, each one of these represents some player here, a particular player. And so there's no information given me. If I knew their age, if I knew that they were 35 years old, they could be, any sort of height. If they were 30, doesn't seem to be any rhyme or reason to the height. If they were 20, they could be as tall as a 35-year-old, or a 35-year-old could be taller than them. So age gives me no information about their height, and so I'm going to say there's no correlation there. Some correlations are stronger than others. So this correlation here seems pretty clear. The correlation, though, between rebounds and versus height is not so clear. Though I guess philosophically or theoretically, you'd think that there might be a rebound advantage to someone who is taller. Anyway, this is a very, very weak trend if it is in fact a trend at all. All right, and which variable is better for guessing height? Well, weight. Weight, I would say, is better for guessing height. So that one's got a stronger correlation. Okay, now let's talk about the linear correlation coefficient, R. This thing assigns values to the strength of the correlation. See, so when R equals 1, the correlation is excellent, is perfectly strong. And that gives you all the information you need. So here I've got height in inches, and here I've got height in centimeters. And indeed, if I know somebody's height in inches, I can find exactly what their height in centimeters is. And so these are perfectly correlated. On the other hand, when there's no correlation, such as age and height, the R value is going to be close to 0. Okay, now for some notation. So this is our way of quantifying this correlation. R is a way of quantifying linear correlation. And so just to remember, that's what statistics attempts to do, is quantify the very difficult, what's very difficult to quantify, and tries to do so in a principled, meaningful way, with which you can get results, meaningful results from. Okay, so n is going to be the number of subjects, x is going to be the data. So x1, x2, x3, that's going to be your data values all the way to x little n. And then y is going to be data values as well. Now, these sets, x and y, so the n for the x and the n for the y are always going to be the same, because they are from the same person, from the same people, the same subjects. And we need to plot them, so you're always going to have an x value, you're always going to have a y value. Okay, and then zx and zy are going to be the z-scores of x and y. So you have x, you compute a mean and a standard deviation, and that gives you the z-score. All right, so here is our R equation. And this is one that is fairly easy to compute, at least relatively. This one here is more difficult to compute because you have to standardize your x's and your y's. Okay. Great. So here's a bunch of examples, or 4 examples at least. So your correlation coefficient is always going to be between -1 and 1 inclusive. Now if it's +1, if it's close to 1, then that means it's strongly correlated, which means you can predict really well. See, if I knew that the x value was this value, x0, then look at how confident I could be that my y value is somewhere in that band, because the data suggests a very strong correlation. And so the greater R is, the more predicting power x has on y. This one here, there's very little predicting power. Well, there is some predicting power, but it's really quite small. See, you have this band here that's rather large, for which you're... Now, it's different from over here, right? It's a different band, but it's still very large. Okay, so R gives you that. Now, if it's a negative correlation, then your R value is going to be negative. And if there's no correlation, then your R value is going to be very close to 0. All right, multiplying each value of the data set by the same number doesn't change R. And we saw that, we see that here in this equation. If I multiply every single x value by something, if I multiply it by A, well, the A can factor out. The A can factor out of all of that, so just an A on top. The a can factor out of all of these sums, only it's going to be an a squared. But outside of the square root, it'll just be a. If I factor it, if I pull it out of the square root, that's just going to be a, and those a's will cancel. And so it does not matter if you scale your x's and your y's, you're still going to get exactly the same r value. And so what that tells us is that r has pretty much nothing to do with slope. R has pretty much nothing to do with slope. Okay. Okay, great. Interchanging x and y also does not change the r correlation. See, there is symmetry here between x and y. If I switch x and y, I will get the same thing. Okay, so this only, and it also only tells you the strength of a linear relationship. Okay, so this correlation coefficient is not to be used in case you had something that looked like, you had your data and it looked like this. Some sort of a nonlinear pattern. You would not use the R correlation to test the strength of that. Okay, you wouldn't use the correlation coefficient to test the strength of that. Okay, and then another thing is that R is very sensitive to outliers. So if you have an outlier, that's going to make your correlation coefficient much smaller than it otherwise ought to be. Okay, now this I want you guys to fill out. This is one of the differences between what we did in class and what we do here. So go ahead and fill this out. Put these values here, your best guess. I am grading it on completion. All right. The hypothesis test. Okay, so we have data, we have, let's see, is this exactly the same as what I had before? I wonder if I should have deleted this. Does age, height, no correlation. Oh, that's, okay. All right. Is there a significant linear correlation? Okay, so when it comes to the hypothesis test, which is, hypothesis tests are sometimes referred to as statistical tests for significance. And that's what we want to know here, is if is this significant. So, n is the number of points. This is the data set of one variable. And this is the data set of another variable, of the other variable. R is the linear correlation of the sample, and rho is the true linear correlation coefficient of the population. And so it is on this which we wish to infer. Okay, so is there a significant linear correlation? That's the question. Well, first we write our claim. Usually, is it correlated or not? Then we negate the claim. Then we form the null and alternative hypotheses. Now, the null hypothesis is going to be always equality, and it's going to be no correlation. We're going to say rho equals 0. Rho equals 0. And this right here is the alternative, which is the opposite, which is going to be rho does not equal 0. And we're usually just going to stick with rho does not equal 0. You could alternatively use this as a null hypothesis, which says that the correlation is positive as opposed to being negative. If that's the case, then you're going to have a right-tailed test rather than a two-tailed test, but everything other than that will be exactly the same, and I'm confident that you all know what to do in that case. If our original claim was that there is a negative correlation, then our null hypothesis would be that rho equals 0, and our alternative hypothesis would be that rho is less than 0. In which case, again, you would have a one-tailed test rather than a two-tailed test. This would be a left-tailed test. Okay. All right, but the degrees of freedom will be the same. That's n minus 2, and the test statistic here is the same. So we identify the significance level, which, remember, the default is 0.05. And then there's our test statistic. It's a t-statistic, student t. So this is with n minus 2 degrees of freedom. Okay, you find the p-value exactly as you would with any other t-test, and then you would make your determination exactly as before, and you would restate it in non-technical terms. Okay, some requirements. First, you want to make sure that the data is randomly selected. You want to make sure that the data at least looks linear, and that the data has no outliers. You want to graph it and check and see if has outliers. What would an outlier look like? Okay, here's my data, and then that's an outlier out there, and that's going to affect the correlation coefficient. Now, there are ways to determine the effect that an outlier has, and to determine whether an outlier ought to be eliminated. But we're not going to discuss that very much. We're not going to discuss that in this class. Okay, but there is of course theory behind that, and I think you would have the tools to do that if you wanted to, if you had to. Okay, now what I want to do is I want to take an example, and so for that I'm going to go back to Canvas. And I'm going to go to the front page. I'm going to go down to the spreadsheet. I'm going to click on that. I'm going to share it into Excel. There's Excel. There we go. Alrighty, so here it is. Cars. Alright, so this sheet provides, okay, well let's just look at what we had before. So the first data set is in the Excel spreadsheet provided for this video, gives the result of a study from the 1920s, interestingly enough, about 100 years ago. The data given the speed of cars, and the data gives the speed of cars and the distance taken to stop. Does there appear to be a correlation between speed and stopping time? I guess this ought to be stopping distance. My apologies. Stopping distance. Okay. If so, is it statistically significant at the 95% confidence level? Okay, let's take a look. All right. So there's my data, and I'm going to do a hypothesis test now. So step 1, the original claim. Did it save? Let's see, save. Save. Oh goodness, what's wrong? Save. My internet connection working? Looks like it's okay. Alright. Save on my iPad. There. Ooh, okay, here we go. Step 1. The original claim. Speed is statistically correlated with stopping distance. All right. Step 2, the opposite of that. Speed is not correlated with stopping distance. Step 3. H naught I need to get that Greek keyboard on my iPad. Okay, rho equals 0. This is going to be no correlation. Alright. H1 is going to be rho does not equal 0. It's going to be correlation. There is correlation. Okay, step 4. Alpha equals 0. That's given to me in the question. Step 5. Test statistic now. Alright, now for the test statistic, all I need is R and N. So I'm going to go ahead and get R. R equals correlation. Here's my data, speed, comma, my distance. Okay, there's my R value, 0.8. Very nice, close to 1, isn't it? I think there's probably going to be a correlation here. Alright, R is that, and then what? Oh, we need N. N equals, okay, equals count. What's the count? Right there? Enter. Alright, 50. Great. So T equals, alright, what is T? There it is, R over and then that square root stuff. So I'm going to get equals R divided by square root parenthesis 1 minus R quantity squared, R squared divided by N minus 2. Oh, N is, I want the cell, minus 2. Close that. Let me just double check. Yeah, that looks good. Enter. Okay, 9. All right. Okay, that's my test statistic. So I move on. Step 6 is p-val. 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 Okay, what do we have here? This is going to equal, now it is a t-test, so I'm going to do t.dist dot 2t, for it is a two-tailed test. I do equals that, and then n minus 2. Okay, looks good. Well, that is very, very small. A very small p-level. So step 7 is p-val less than alpha? And the answer to that is yes, significantly. And so I'm going to reject the null that there's no correlation. There's definitely correlation here. Step 8. There, whoops, not there. There is evidence to support a statistically significant correlation. A statistically significant correlation between speed and stopping distance. Let's see, between speed and stopping distance. Is there anything I want to add to that? There is a There is evidence to support a statistical correlation between speed and stopping distance. Okay, that's fine. All right, there it is. Great. So there's my hypothesis test. So there is that correlation. All right. Done. And that was at the 95% confidence level. Okay, now another useful thing is this regression line. When a correlation is suspected, we would like to try to predict one of the variables given another. So correlation means one variable has information contained in it about the other variable. We would like to leverage that as much as possible. What's the best approximation we could make of one variable given the value of another? And this is called regression. All right, or prediction would not be a bad way to fill that in either. Okay, so the line of best fit, or this least, in this case we're going to use the least squares regression line, is this line, y equals b1x plus b0, where b1 equals r, that's my correlation coefficient, times the standard deviation of y, the standard deviation of y, divided by the standard deviation of x. And b naught is going to be, when you solve for b naught, the y-intercept. So what we want to pick b naught so that y hat equals b1 x hat plus b naught. And so we solve and we get, that's where our b naught comes from. Okay, now once we have that relationship and it is the best fit, it's the one that does the best job minimizing the error that between predicted and actual, we can put in some data value x tilde and get a prediction for y, which would be y hat. Okay, let's do that on our. Okay, so we can do that. Now I just want to make one observation here, and that is that so y hat is going to be this approximation of y given some information x tilde, not x bar, x tilde. And so what that means is that the variance, right, standard deviation squared, the variance of y hat is going to equal, so if you do this variance calculation using this data here, you're going to end up getting b1 squared times the standard deviation, or times the variance of x. Now, b1 squared times x squared from this formula here equals r squared times sy squared. And so what that tells us is that the variance predicted by the x variable, so we are going to predict the y variable using the x variable, and that's going to give us some variance. The variance predicted by the x variable is a full r squared of the actual variance of y. So here's the actual variance of y. You need to multiply that by r squared, which is less than 1. And that gives you the amount of variance that's predicted by the x variable. Okay. So here's interpolation and extrapolation. What are they? Well, interpolation is when is using linear. Okay, interpolation is using the linear model to predict y values between known data points. So here's my data points. Here's my best fit line. if I wanted to find my x value that went with this one, I could use that. This is called interpolation because I have values on the right, I have values on the left, and I'm just using my best fit line to do that. Now that's okay, right? Because it would appear that the pattern continued. Extrapolation, well, that's a bit dangerous. Extrapolation, you have this data here, and it maybe goes like that. And then what you want to say is that this one way out here, outside of the realm for which you have data, and you're going to say, well, that's going to be right here, and that's going to be the y value I should expect. That in general is a bad practice. It can be done, and in fact it is done quite a lot, but pains are taken to make sure that it is done sensibly. And we're not going to talk about that in this class, but I just want you to know that right there is so extrapolation is using linear model to predict y values beyond's the word here, beyond known data. And this is problematic, as the following slide shows. So here's somebody extrapolating way beyond the available data. Here's somebody extrapolating backwards. And that brings us to our next slide. And so, our next example, we can now complete this cars example. So this is example 1.5. And what we want to do now is we want to use a regression line to predict the stopping time for a car going 21 miles per hour. All right, so how long is it going to take that car to stop? And so let's do a regression line. Okay, now one thing that I failed to do on the onset of this problem was just simply plot and get an idea of whether this is linear or not. Whether it's sensible to even check that it has a linear correlation. So what I'm going to do is I'm going to select that data. I'm going to go to Insert. I'm going to go to Charts right there. I'm going to go to Scatter Plot. And pick that first one. And there it gives me a nice scatter plot. Look at that. A linear correlation? Yeah, possibly. Could be. Okay, so there's my chart. Okay, now I'm going to do my my best fit, my line of best fit. Best fit. Okay, well, what I need is B1 first. And B1 is going to require, I'm going to need SX, not SO, SX, and that's going to be stdev.s of now which do I want? I'm interested to know the distance. Speed is easy enough to get. I'm going to get the speed, but what's difficult to know is my stopping distance and how long that's going to be. So my x value is going to be speed. All right. So there's my standard deviation for that one. Sy is going to equal stdev dot what do we have here? Dot s of, and now I take my my response variable. So you could think of sx as your explanatory variable, and this one's your response variable. And then I need r. Okay, so I'm ready to do b1. So b1 is going to equal, let's see now, I want an output of y, so I'm going to do y divided by standard deviation of x times, and I need to go back up here and get r. There's r. Enter. All right, there it is. So it's the ratio between the standard deviations with x on the bottom, because you want x to be canceled out when you multiply by your x value, and then you multiply by r. So there's your b1. Now what we need is b0. Now before we get b0, we need, let's see now, before we get b0, we need x bar and y bar equals, okay, x bar, and x bar is this one. Oh, I forgot to do average. Alright, let's see if I can do this without it being too painful. Let's see. Oh, mercy. Okay. Come up here. Alright, enter. Okay, that looks okay. And then y bar is going to equal this thing here, equal average. Enter. Okay. And now y bar is going to equal, let's see, no, b naught is going to equal y bar minus b1 times x bar. Alright. So that's my b naught. Okay. Now what I would like to do, I've got this extra column here. I'm going to go this estimate. That is going to equal b1 times my x value plus b naught. It's right there. Alright, but I want these to have dollar signs. So dollar sign Alright, what's going on here? Plus alright, dollar sign there. Just put a dollar sign here. Okay, so that's great. And then this one, here's my x. Alright, no dollar sign there because I want that to change as I move the cell that I'm in. So I'll multiply this by dollar sign. See, is this going to work? I don't know if this is going to work. Yeah, no, it didn't work. Okay. B naught. But, oh gosh. Okay, B naught, and I'm going to click, there we go. Dollar sign right there. I'll go ahead and put a dollar sign there. Okay, great. Alright, so according to this model, when the speed is 4, my stopping distance is negative 0.84. So that doesn't seem very good. Let me just make sure that's right. So there's A10. That's it. And there's B naught and B1. Did I switch those? B1. No, it looks okay. Alrighty. Let's see. Command C. Shift. Go all the way down here. Okay. Command V. Alright. So, okay, and now let's plot it. I'm going to click on my graph here, And now I'm going to move my data over one. Okay. Alright. Click on the plot. I'll pull my data, drag my data over. Does not want me to. There. Okay, so not a bad line of best fit right there. So those are my predictions. Okay. Now, the problem said what's the stopping time? What's your best prediction for the stopping time when the car is the stopping distance when the car is going 21 miles per hour? All right, so for that I'm going to put 21 for x, which, you know, maybe I'll go ahead and put it right down here. So 21 for x. This thing here I don't know, but this thing here I could find. Command C, Command V, and that's 65. And that's not such a bad. Look at these 2 points here. When it was 20, the actual stopping time was 64. When it was 22, the actual stopping time was 66. So it is in between those. So I think that's actually seems to me like a really great estimate. And so that's my estimate there. Okay, let's go back now to this and let's answer these questions. Does there appear to be a correlation between speed and stopping distance? Yes. There is correlation. It's quite significant. Use a regression line to predict the stopping time for a car going 21 miles per hour. Okay, well, a car going 21 miles per hour will probably take 65 feet to stop. All right, I don't know if it said it, but the stopping distance is in feet. Okay, great. All right. Okay, that's that. So the next example I'm going to do is optional, so you don't have to do it. But yeah, that's it. That's it for now. Okay, so yeah, that's that. All right. Let's go ahead and do this example. The Excel spreadsheet contains real data from the distance of the planet Neptune, for the distance from the planet Neptune, along with the rate of burglaries in Kansas. Does there appear to be a correlation between the data? If so, find the linear model relating the distance of the Earth from the distance that the Earth is from Neptune, and the rate of burglaries in Kansas. About what burglary rate would you expect in 2025 when Neptune is 29.9034 astronomical units away from Earth? All right. So I'm going to go back to my data here. Going to go to burglaries, and here is the average distance the Earth was from Neptune for the years given, And we look up, and this is according to the FBI criminal. They've got some database online, and so there's that. So I think this right here is number of burglaries per capita per year, and this one right here is the average distance. So average distance. This is number of burglaries per capita per year. And so, and let's see, per capita might not be the great, maybe per yeah, no, that might be per capita, so total, but it's got a decimal there, so the data would need to be looked into a little bit more as to what exactly this is telling us. Okay, well, let's start with a scatter plot now. All right, so I'm gonna grab this. Whoops. Go to home, go to insert, go to chart, scatter plot. Let's take a look right there. All right. Very interesting. So looks like, well, maybe there's a trend. It doesn't necessarily look linear though, but let's just see if a linear correlation fits and agrees with it. So what? So what do we do? So let's go ahead and test first of all to see if this linear correlation is statistically significant. Step 1. Their original claim. There is a correlation between, and if this is a statistical correlation, we're not proving that they are related. It's just that statistically, according to the data, that there may be a relation. Statistically, there is a statistical correlation between the distance of Neptune from Earth and the rate of burglaries in Kansas. All right, great. Okay, step 2. Opposite of the original claim is there is no correlation. All right, step 3. H naught, my null hypothesis, always needs to have equality. H naught is going to be rho equals 0. Let's see now. Let me take that backslash out. Rho 1, or H1, is going to be rho does not equal 0. Step 4, my alpha is going to equal 0.05, excuse me. Step 5 is the test stat. Test statistic. All right, what do I need for this? Well, I need R. I need R and I need N. Corel. Thank you, Excel. there's my first array. Here is my second array. Whoopsies, I think something happened. Yep, something happened. There it is, 0.96. Can you believe it? Boy, that is strong. I think we'll see that is strong. Right, n equals, oops, I need to count. Count. Down here, right there, enter. 38, okay. T equals, okay, now, equals r divided by square root 1 minus r squared, whoops, where'd my r go? R squared divided by n minus 2. Close parentheses there. 21. That's a huge test statistic there. Step 6. P-value. I'll bet it's going to be super small. P-value is going to equal t.dist dot 2t of that test statistic with degrees of freedom that minus 2. Enter. 10 to the negative 22nd. That's very, very low. Step 7 is p-val less than alpha. Okay, let's check. Is p-val less than alpha? Answer, yes. Yes, it is. Reject the null hypothesis. There's no way there's not a correlation. Those are definitely statistically correlated. Okay, step 8. There is evidence to suggest. All right, let's do support. I don't use support enough. Support, I don't use that term nearly enough. Support is stronger than suggest, I think. There is evidence to support to support a significant statistical correlation between the distance of Neptune from the Earth and the crime, burglaries, I guess I should say, and the burglaries in Kansas. Okay, now this is a spurious, this is a spurious relation. There really isn't any relation between the distance from us to Neptune and the crime in Kansas. And so you have to take it with a grain of salt, right? It says that there's a correlation, and there is a statistical correlation, but that doesn't mean that they are related. It doesn't mean that they're related. It doesn't mean that one depends on the other. Okay. It just means that it's a statistical anomaly, which happens to, which the data itself is significant. Okay. Alrighty. Let's do the line of best fit now. So in order to do that, I need a few things. I need x, I need sx, and that is going to be equals stdev dot s. Come over here. So the distance is going to be the explanatory variable. Enter. I'll do x hat while I'm at it. The average of the explanatory variable. I didn't do average, did I? Equals average of my explanatory variable. Go, enter. All right. Sy equals stdev.s, this stuff right here, y hat equals, oh, yep, there, beginning to expect when it's going to change that on me. Sy hat is, okay, equals average, this stuff, the burglaries. Enter. All right. B1 is going to equal R. Where's R? Equals R, which is right there, times Sy over Sx. Enter. B0 is going to equal y hat, see, equals y hat minus b1 times x hat. Okay, so there it is. Great. All right, now let me do my predicted. So this is my estimated burglaries equals b1 times my x is this one plus b0. Enter. And then I'm going to drag. Oh, wait, before I drag, I need to put in my dollar signs. Dollar sign there, then here, dollar sign. Okay, great. Now I can drag. Command C, Shift, down. Command V. All right, now I'm going to click on my plot. I'm going to extend my data. And there it is. Pretty good fit. Pretty good. All right, and so what about when Neptune is 29.9034 units away? So let me go ahead. 29.9034 astronomical units away. This one I don't have data for because it's in the future, but I can estimate it. And this is extrapolation. But I'm not extrapolating too far away. Not if I type in the number correctly. All right. Equals, and you know what? I'm just gonna Command C. Put that here. Command V. Oh brother. Command C. Oh. Command C. Copy. Command V. There it is. 300. About 315. Burglaries per capita. Yep. All right. about 315. So that's what we're looking at there. Okay, everybody. That's all I wanted to talk about today. So get ready to, yeah, anyway, so there's your example. All right. Everybody have an excellent day. We'll see you in class.